Hey everyone. Back in school, did you ever get the feeling that your math teacher was keeping something from you? You were handed formulas like little magic spells. Memorize this one. Use it on the test. Forget it by summer. Almost nobody told you where any of it came from, or why anyone had needed it in the first place. And underneath all of that, most of us picked up a quiet belief. Math is the one place where everything is clean. Every question has an answer. Every number follows a rule. That belief is comforting. It is also not quite true. The real history of math is not a straight road. It is a series of moments where somebody ran into a number that broke their intuition. Numbers that got called impossible, or absurd, or dangerous. Numbers that people argued about for 100 years before accepting them. Today I want to take you to the strangest one of all. There is a number sitting between 0 and 1. It has a name. It is called omega. It is defined with complete precision. A mathematician can tell you exactly what it means in one sentence, and there is no fuzziness in that definition anywhere. And nobody can ever compute its digits. Not you, not me, not the fastest supercomputer on Earth. Not any machine that could ever be built. That is not because we are not clever enough yet. It has been proven. So how can a number be perfectly defined and permanently unknowable at the same time? To feel why, we have to walk back through the moments when math almost fell apart. Let me start somewhere that sounds too simple to be worth asking. What is a number? Most of us met numbers as tools. 3 apples in a basket, 2 meters of rope. A number was a label for an amount of stuff you could point at. If you ever sat in a classroom wondering why we suddenly needed negative numbers, or something called an imaginary number, and the only answer you got was that it would be on the exam, your doubt was completely reasonable. That was a good question. It just never got answered. Here is the answer. New kinds of numbers almost never showed up because somebody wanted a better counting tool. They showed up because the old numbers ran out of room. The pattern is always the same. Someone asks a question that is perfectly legal inside the system. The system has no answer for it, and rather than let the whole structure crack, mathematicians are forced to widen what the word number is allowed to mean. So numbers are less like a set of tools and more like a record of past emergencies. Every strange one you learned in school is the scar left behind by a crisis. Let me show you 2 of those crises. Then I will show you the one that never healed. Start with a square. Every side is 1. Now draw the diagonal, corner to corner. How long is that diagonal? The Pythagorean theorem tells us. In a right triangle, a squared plus b squared equals c squared. Here a and b are both 1. So the diagonal squared equals 1 plus 1, which is 2. The diagonal is the square root of 2. Nothing about this is exotic. You can draw it on a napkin. Here is the trouble. The followers of Pythagoras in Greece around 2,500 years ago held something close to a religious doctrine. They believed every length in the universe could be written as a ratio of 2 whole numbers, some number on top, some number on the bottom, a fraction. So the diagonal of the simplest square in the world should be a fraction, and it is not. Here is why. Suppose the square root of 2 really does equal some fraction a over b. And suppose we have already canceled that fraction down as far as it goes, so a and b are not both even. Square both sides. You get 2 equals a squared over b squared. Multiply across, and a squared equals 2 times b squared. So a squared is an even number. And if a squared is even, then a itself has to be even, because an odd number times an odd number is always odd. So write a as 2 times k. Then a squared is 4 times k squared. Put that back in. 4 times k squared equals 2 times b squared. Cancel a2 from both sides, and b squared equals 2 times k squared. Now b squared is even, so b is even too. But we started by saying A and B were not both even. They are. There is no way out. The square root of 2 cannot be a fraction. Not because nobody has found the right one yet, because there is none. That is a real proof, and you just followed it. There is a famous story attached to this. A Pythagorean named Hippasus of Metapontum, living in the 5th century before the Common Era, is said to have let this secret out and to have been thrown into the sea for it. I want to be honest with you here. Historians still argue about that story. The ancient sources are thin. Some of them never name Hippasus at all, and some say he drowned over an entirely different secret. The tale survives because of how the discovery felt, not because anyone kept the records. Now, the second crisis, and this one has a beautiful payoff. In the 16th century, Italian mathematicians were hunting for a formula that solves cubic equations. Take this one. X cubed equals 15x plus 4. You can find a solution just by looking. Try x equals 4. 4 cubed is 64, and 15 times 4 plus 4 is also 64. It works. The answer is sitting right there, an ordinary whole number. Girolamo Cardano published the general formula for equations like this in his book Ars Magna in 1545. And when you feed this particular equation into that formula, something disturbing happens. The formula routes you straight through the square root of negative 121. There is no such thing. No ordinary number, multiplied by itself, gives you a negative. Cardano knew that. He called work with the square roots of negatives a kind of mental torture, and he set them aside as useless. 27 years later, Raphael Bombelli picked the problem back up in his book L'Algebra in 1572. He tried something that sounds like cheating. He said, "Suppose the square root of negative 1 is a real object. I do not know what it is. I only insist that it obeys the ordinary rules of algebra. Watch what happens. The square root of negative 121 is just 11 times the square root of negative 1. Now take the quantity 2 plus the square root of negative 1 and cube it. First square it. You get 4 plus 4 times the square root of negative 1 plus the square root of negative 1 squared. That last piece is negative 1. So the whole thing is 3 plus 4 times the square root of negative 1. Now multiply that by 2 plus the square root of negative 1 one more time. You get 6 plus 3 times the root plus 8 times the root plus 4 times the root squared. The root squared is negative 1 again, so that last piece is negative 4. Collect it all up. You get 2 plus 11 times the square root of negative 1. Which is exactly the thing sitting under Cardano's cube root. Do the same with the minus version, and you get 2 minus the square root of negative 1. Cardano's formula tells you to add the two cube roots together, so add them. The impossible parts cancel each other out. 2 plus 2 is 4. The formula was right the whole time. It just insisted on walking through a country nobody believed existed. And here is the payoff. Imaginary numbers are not imaginary in the sense of made up. Picture the number line. Multiplying by negative 1 flips a number to the other side of 0. That is a half turn, 180 degrees. Multiplying by the square root of negative 1 twice has to produce that same half turn because that is exactly what its definition says. So one multiplication by it must be half of a half turn, a quarter turn, 90 degrees. That is what this number does. It rotates, and the moment a number rotates, it cannot stay on the line anymore. It steps off into the plane. So all these strange numbers had one thing in common. However weird they looked, we could still compute them. You could calculate the square root of 2 to a billion digits tonight. In the 20th century, somebody found a much darker limit, a place where computing itself gives. Before we go further, I need one idea in place, and it is not a math idea. A computer program is a recipe. Step 1, do this. Step 2, do that. If the eggs are not stiff yet, go back to step 2. Some recipes finish, some do not. If I write, keep stirring until the sugar turns blue, you will stir forever, because that never happens. The recipe is perfectly clear. It simply never ends. In 1936, Alan Turing published a paper with a heavy title, On Computable Numbers, with an application to the Entscheidungs problem. Inside it, he asked a question that sounds almost practical, like something a software company would pay for. Could there be one master program, call it H, that reads any other program and tells you correctly whether that program will finish or run forever? That would be enormously useful. Turing showed it cannot exist. Here is his argument, and it takes about a minute. Suppose H exists. It always answers, and it is never wrong. Now I build a small troublemaker. Call it subversive. Subversive does exactly one thing. It hands its own code to H and asks, will I finish? If H answers that it will finish, subversive immediately drops into a loop and runs forever. If H answers that it will run forever, subversive immediately stops. Now ask the question, does subversive finish? If it finishes, then H must have said it would run forever. But H is never wrong. That is a contradiction. If it runs forever, then H must have said it would finish. Wrong again. Every path ends with H being wrong about something, and we assumed H is never wrong. The only thing left to throw away is the assumption. H does not exist. Sit with that for a second, because it is stronger than it looks. This is not a case of we have not built H yet. It is not a case of needing a faster machine. A perfect halting detector is not a hard engineering problem. It is a logical impossibility, in the same way a square circle is. There are questions with definite yes or no answers that no procedure can ever settle. That conclusion is forced, not chosen. Turing's result sounds like a philosopher's word game. Then, in 1975, a mathematician named Gregory Chaitin did something to it that nobody expected. He squeezed that entire impossibility into a single number. Here is how you build it. Imagine we write programs by flipping a coin. Heads is 1, tails is 0. Flip a few times, and whatever string of bits comes out, that is your program. Most of the time you get garbage. Sometimes you get something that actually runs. Omega is the probability that a program made this way stops. That is the whole definition. It is a probability, so it lives between 0 and 1. Let me make it concrete with a toy world. Suppose we have a tiny programming language, and only 3 valid programs exist in it. Program A is the bit string 01, 2 bits long. It runs and it stops. Program B is the bit string 110, 3 bits long. It runs and it stops. Program C is the bit string 10, 2 bits long. It loops forever. What is the chance a coin gives you program A? You need 2 specific flips to come out right. 1/2 times 1/2. That is 1/4 or 0.25. Program B needs 3 specific flips. 1/2 times 1/2 times 1/2. That is 1/8 or 0.125. Program C also has a chance of 1/4, but it never stops, so it contributes nothing. Add up only the ones that stop. 0.25 plus 0.125 gives 0.375. In that little world, omega equals 0.375. Nothing mysterious happened. We just added up the odds. The real definition is that same sentence with everything filled in. Omega is the sum, over every program that halts, of 1/2 raised to the power of that program's length in bits. Let me be straight with you about one simplification. To make this work properly, you need a particular way of encoding programs, called prefix-free, so that the probabilities add up correctly and never pass 1. And omega depends on which computer language you fix at the start, so there is not one single omega. There is one for each machine. I am skipping that machinery. The logic underneath is exactly as I described it. Now, the part that should bother you. Omega is a specific real number. Fix your machine, and it is pinned down. It is not vague, and it is not undefined. It has a first digit, a second digit, a thousandth digit, all of them sitting there waiting. And to know those digits, you would have to know which programs halt, which is precisely the thing Turing proved nobody can decide. So omega is unknowable. Watch how far that goes. Suppose someone handed you the first few thousand bits of omega. With them, you could settle any halting question about programs shorter than that. Here is why that matters. Take the Goldbach conjecture, the old claim that every even number above 2 is the sum of 2 primes. Nobody has proved it. I can write you a short program that grinds through the even numbers one at a time, hunting for one that is not a sum of 2 primes, and stops the moment it finds one. That program halts if and only if Goldbach is false. So if I knew enough of omega, I would know whether that program halts. And I would know whether Goldbach is true, without proving anything at all. The same trick works on the Riemann hypothesis, and on a long list of other open problems. That is what omega holds. A compressed answer key to a huge slice of unsolved mathematics. And that is exactly why you cannot have it. A number that answers everything cannot be computable, because if it were, all of those questions would already be closed. So its digits behave like pure noise. They are provably random in the strongest sense we have. No pattern, no formula, no shortcut, nothing you could compress into a rule. To get the millionth bit, there is no method better than guessing, and your guess is worth exactly one coin flip. Randomness, produced by logic itself, sitting inside a number that is perfectly defined. If this feels familiar, there is a reason. In 1931, Kurt Gödel proved something that shook mathematics. In any consistent system of rules, strong enough to handle ordinary arithmetic, there will be statements that are true and that the system cannot prove. Not hard to prove, cannot. For a long time, that result lived at a distance, wrapped in careful logic, easy to file away as a technicality about self-reference. Omega drags it into daylight. Chaitin showed that a set of axioms carrying a certain amount of information can only ever pin down about that many bits of omega, and no more. Add more axioms, and you buy yourself a few more bits. You never finish. So the incompleteness that Gödel described is not a rare defect hiding in some exotic corner of logic. You can point at where it lives. It lives in the digits of one number between 0 and 1, and it runs on forever. I do not think this is a reason to feel defeated. It is closer to the opposite. Mathematics turned its own tools on itself, asked how much it could possibly know, and got back a precise answer. Even the boundary of our knowledge has a shape we can describe. That is a strange kind of achievement. Look at the road we took, a square with sides of 1 and a diagonal that refused to be a fraction. A cubic equation whose only honest route to the answer 4 ran through the square root of a negative number, and omega, a number defined in one clean sentence, whose digits are locked away for good. None of these were errors in the system. Each one was a door. The square root of 2 opened up the continuum. The square root of -1 opened up the plane. Omega opened up the edge of what can be known at all. Which brings me back to where we started. Math is not a pile of arbitrary rules handed to you to memorize before a test. It is a structure so honest that it will tell you precisely where it stops. If you enjoyed following the strange numbers out to the edge, subscribe and come along on the next one. And leave a comment with the idea you want explained next. There is a good chance it turns into the video we make.